Welcome to December 30th LeetCode challenge. Smallest integer divisible by k. Given a positive integer k, you need to find the length of the smallest positive integer n such that n is divisible by k. N only contains the digit 1. Return the length of n. If there is no such n, return -1. Note that n may not fit a 46-bit signed integer. Alright, so this sounds like a math question here. So our approach is going to be a math type approach, mathematical. So given example number 1, let's kind of break down what we're looking for and how to approach it. You have k equals 1. The output will be 1 because the smallest integer, smallest answer is n, which is 1, which is has a length of 1. Right? You give the number 2, the smallest number that you can divide by. There's no positive integer n divisible by 2. And that makes sense. You can't divide anything. There's no smallest integer n divided by 2. If you give me k, the output would be 3 because the smallest n value that you can get is 111, which is the length of 3. So that makes sense, actually. Yeah. So k is between 1 to 10 to the 5. Okay. So basically, what we want to do is find the smallest integer divisible by k, and we want to find the length of the smallest positive integer. So that means where n only contains digit 1, right? Because if we take k equals to 3, and we find that the smallest answer is n, which means that the length is size 3, and it contains 1. That means that we smallest integer divisible by k. Let me see. Yeah, so basically it only contains the digit 1. That's the constraints here. See, where n only contains 1. So from this little blurb here, we know that a number can only contain 1. A number containing only 1s cannot be divisible by 2 or 5. Right? Any number that's k equal to 2 or 5 cannot be divisible. And you can convince yourself that's true, such that here's just a note here. A number divisible by 2 can only end with 0, 1, 2, 4, 6, and 8, or 8. Alright? And a number that is divisible by 5 can only be only end with 0 or 5. Right? And that's a fact that we can recognize already off the bat from the question given, and also the example given as well. So that means that to solve the problem, so we don't have and also we could also convince, if you look at the hint here, I think we never get a remainder of 0. Why would that happen? How would we know? So that's like a remainder. We will never get a remainder because Python supports arbitrary large numbers. So, however, so using, I guess, large numbers, Python's built-in large big integer type ability where it may not fit a 46 signed integer. That means it has to be a unsigned, right? So that's why we'll never get an overflow or a remainder from that. So let's start with a naive approach. A naive approach would be, let me just, I'll erase this. So if, and let's see if hint number 1 helps. Use 111, blah blah blah. We only use stored remainder module k. So we use a modulus function. So if not k is k modulus 2, excuse me, or not k modulo 5, we are going to return -1. This is from what our observation was before. So next thing we want to do is find the length. So n equals the length, which is going to be equal to 1 for now. I spelled length wrong. So while true, we are going to iterate through if not n modulo k, then we're going to return the length, which is going to be 1 at the moment initially. And then if that's not if n is the modulus of k, then we pass through it. Then that means that the length will be incremented by 1. And then we also want to take, we want to use this function right here. This little hint that they gave us, which is going to be n is going to be equal to n times n plus 1. We don't want to return 1, we want to return the length. Let's run this code. So this approach makes use of Python's big integer type of approach, where we're solving so the remainder does not exist using this fact here, where we have this function. Since Python does support arbitrary large numbers, however, it comes at a cost of speed and time, but this is a naive way of doing it. Can we make this a little bit easier? Let's submit it first and see what works. Oh wow, that does take a long time. Hope it works. Oh no. All right, let's try to optimize this a bit. Let's see. That's good. Oh, what the? That's supposed to be a 5. All right. So let's use the math here to help make this speed a little quicker. So one thing we know is that after every iteration we have here, every time this while loop runs through, we have we're using math here. We just say n equals to k q plus r. So this is basically we have some constant for a quotient plus the remainder. And therefore, we know that our little what's called function here, where we have n equals to n 10 times n plus 1, we know that that is going to be of the form, well actually we'll just type it out. So 1 is going to be 10 times, so n is going to be, we just substitute n from the previous line into it, k plus r plus 1. And what we can do is we expand that out using mathematics. 10kq plus 10r and then plus 1. Alright, so we have a mathematical equation there. So we know that the first term is divisible by k. And so for this given this is plus 1. So the first term here is divisible by k. So therefore this term right here is also should also be divisible by k. It depends. So that means if this first term here is divisible by k, that means that I'll just write it out actually. 10k q is divisible by k. That means that the remainder 10. This implies that 10r plus 1. If this function here is divisible by k, then this term right, the last two term, is all depends whether actually it implies that this term right here, 10 star n plus 1, is divisible by k depends on this term right here. So this is divisible. If this is obviously divisible by k, which implies that this is divisible by k only depending on whether 10r plus 1 is divisible by k. Right? This is kind of a mathematical induction. Therefore, we need to keep track of the remainder. Right? Keep track of the remainder. And then we just kind of add that a little bit of definition to what we have so far, and it should work. So let's say we have instead of keeping track of n, which is not what we need anymore, right? N is important, but n is only divisible by k if the remainder expression here is divisible by k. So we're going to keep track of that instead, and then we are going to do r modulus modulus k. And then, therefore, replacing all the n terms, we don't need that anymore. We'll take care of everything with respect to r, and therefore, we are keeping track of the remainder. Let's erase this and run. Submit. I hope this works. Awesome. Jeez. Scared me a bit. Alright. There you go. Time complexity is big O of n, because there's this while loop here. It has to iterate through each of the modulus of k, right? Which is not that much actually. Well, it could be a lot. I mean, depending on yeah, it could be a lot. Space complexity is constant space because we store everything inside variables. Alright, that's it. Have a great day, guys.